Okay. Do I just flip in through? Or do I wait? What do I point it at? Oh, I flipped too far. Okay, so first of all, thanks so much to the organizers for inviting me. I'm really happy to be here and to be representing such a huge and diverse group as I am here. Just a couple of things about myself. So I'm mostly coming from a very awkwardly named center called the Center for Robust Decision Making in Climate and Energy Policy from the University of Chicago, which is my home base. But just to make myself very mysterious, I like to put all of my adjunct and guest and visiting affiliations on there as well, so people think I come from all over the world. So I'm also at University of Chicago and Argonne and Columbia, and I even have a position at London School of Economics. So very mysterious. Where am I? Yes. Quick acknowledgments. There's an absolute ton of people who have contributed to the work that have gone into these talks through various different centers. So this is the logo for the RDCEP Center at the University of Chicago, which involves dozens of people. Of course, the Agricultural Modeling Intercomparison and Improvement Project, which I think last I checked is a network of 700 or 800 modelers from around the world. And then the Intersectoral Impacts Model Intercomparison Project, which is led out of the Potsdam Institute for Climate Impacts Research and also YASA, and involves many more dozens of modelers. And we heard a little bit about that earlier from Sari about the health side of it. Support from lots and lots of people. I tried to include a list of everyone who would actually at least be in the audience today. And of course, I forgot one key one, which was NASA. So Cynthia Rosenzweig is going to kill me when I get back to Columbia, but that's okay. Hopefully she'll forgive me. A quick plug for a couple of things from the RIDSIP Center. So one of the things we do at the RIDSIP Center is we design easy-to-use web-based applications for sort of that people can really use to get their hands dirty on climate economics and on climate change. And since this meeting is all about sort of integration and understanding across disciplines, I just wanted to give a quick pitch for these because I think these are extremely useful tools for people that are outside of climate science or outside of climate economics. The first one is called WebDICE. Most of you are probably familiar with the DICE model, which is an integrated assessment model that Bill Nordhaus invented back in like 1875 or something like that. And we've added lots of different features and assumptions and really enabled people to be able to play around and tweak different assumptions and see what kind of effects it has, build their own policies, and et cetera. Also what we call the climate emulator, which is basically a very robust statistical emulator engine for all of CMIP5 that allows you to take basically the entire ensemble of CMIP5 data, which is the latest climate model ensemble data, and do lots and lots of cool things with it. Look at regional effects in different regions, create your own custom CO2 concentration pathways, and see what the models would say for those. A very, very interesting and cool tool for looking at future climate. Quick introduction. We've already seen my next two slides, I think, at least twice today, but I want to talk about them from a slightly different perspective. So this is, of course, the pathways of global average surface temperature projected over the next 100 years. This is from CMIP5 data. We have only 2 of the 4 RCPs are shown, which is the very severe one, RCP 8.5, and the super happy fun times one, RCP 2.6. And here you can see the levels of uncertainty in each of these different scenarios. And this is sort of representing the level of sort of scenario uncertainty or socioeconomic uncertainty across the different potential pathways, if you think they're all sort of equally weighted in likelihood at least. So lots of uncertainty in global mean temperature, but the point is somewhere in this range of 2 to 4 degrees, maybe a bit higher, is the range of possible global mean temperature changes. But the key thing is that global surface temperature change is not at all distributed uniformly across the globe. And in fact, most relevant for the purposes of my talk are the fact that land surfaces are expected to warm significantly more than ocean surfaces. So that global surface temperature includes both ocean and land warming. And then, of course, there are, strong gradients in various places, especially north to south, with much more warming in the northern zones and less in the southern. With precipitation, of course, we all know that the patterns are much less robust and we don't really know what's going to happen. Although we do start to see some robust patterns emerging in the extreme scenarios, and they tend to go along with the standard sort of rule of thumb. Drier areas getting drier. You can see the Mediterranean getting a bit drier. You can see Mexico in the southwest getting a bit drier. You can see, the drier parts of Australia getting a bit drier, South America, or South Africa, et cetera, et cetera. So tend to follow that same that rule of thumb that we've been talking about for quite a long time in climate science. Dry areas should be getting drier on average, and wetter areas might be getting wetter. All right, so climate impacts. I'm going to give a little bit of a description on climate impacts. I call it climate impacts what we know, just because I wanted to be consistent with the climate change what we know. A lot of what I'm talking about is going to be climate impacts what we don't know, but that doesn't look quite as good on a slide title. So this is a summary. So we have already heard a little bit about this project, but this is a project done in 2012. It's called the Intersectoral Impacts Model Intercomparison Project. It was a partnership of about, I think, 40 or 50 different modeling groups from around the world. Included a lot of efforts from AgMIP and was organized, as I said, out of the Potsdam Institute in Yassa. It included about 40 modeling groups from 4 sectors. Agriculture and also ag-econ type models, so biophysical and ag-econ type models, hydrology, biomes, and then health, which we already heard about earlier this morning. Simulations were done with 5 CMIP 5 GCMs and 4 RCPs and lots and lots of crops for the agricultural sector. So I'm not really going to talk much about models at all in this talk, but rather about applications of models and results from them. So I'll just take this one opportunity to describe a little bit about what I mean when I say models here. So for these global scale analysis, I'm talking about typically global gridded models run at a high resolution, or run at a relatively moderate resolution over the entire globe, a resolution that enables you to pick up, say, river basins and regional, reasonable regional effects, but not the kind of ultra high resolutions that allow you to pick up, urban heat islands and those sorts of lovely things. So I'll be talking at a somewhat lower resolution and mostly focusing on the global. The outcome of this was a 10 or 11 paper, I forget, special issue of PNAS that came out early this year. And I'm going to mention a little bit at some points 4 of these papers. And all this data is available publicly in an easy-to-use, semi-easy-to-use ESGF archive if anybody's interested. So quickly, the first paper is on impacts, was about global agricultural productivity. And I don't want to focus too much on these maps. This project involved 7 global gridded crop models run using 5 GCMs from CMIP 5 and all 4 RCPs. And these were very diverse models run with very diverse assumptions and very diverse conditions. And the general results that were found are sort of summarized here. So we have very robust negative results in the tropics for maize and for wheat, with much more mixed and in fact even somewhat positive results, but with very little, you'll see very little, well, you can't see the hatching very well in these plots at all, but this is hatched to identify model agreement here in these big negative areas, whereas there's very little to no hatching here for rice and soy. We broke these models down into 2 different classes. Roughly half the models that were used in the simulations included nitrogen stress. That either meant that the models modeled the nitrogen cycle and included nitrogen-carbon interactions and explicit nitrogen modeling in the soil, and half the models did not include nitrogen in the modeling. Either they didn't model nitrogen at all, or they included sort of an overabundance of nitrogen fertilization in order to cancel out the effects of nitrogen limitations. And what we find, so we've divided the results here by these model classes. And what you can see if you just sort of squint your eyes, the models that do include explicit nitrogen stress find very, very much more severe effects of climate change in the future. And the models that do not tend to find modest or even positive effects of climate change. And the lessons we learned from that, again, there are fairly robust lower latitude vulnerabilities. CO2 effects are really the key to understanding the future impacts of climate change. So this is CO2 fertilization effects are key to understanding future impacts and also the uncertainty in these projections. And finally, models that incorporate realistic nitrogen see significantly less gains from CO2 effects at present day levels. So this is basically saying that CO2 effects are really huge in these models that don't include nitrogen stress because there's no nutrient limitation from nitrogen, and the CO2 effects end up being quite explosive. Finally, we also looked at the project also included an ensemble of 11 global hydrological models run with the same set of consistent climate scenarios as the crop models. These global models produced tons of different variables, global runoff, and etc. We combined these 11 global hydrological models with the ensemble of global crop models in order to do an analysis of the future potential of irrigation as both an adaptation mechanism and as potentially as an additional negative consequences of climate change. What we found is that water limitations from reduced runoff and hydrological limits across the globe. So just a quick summary. With CO2 effects, with including the effects of CO2, direct losses from climate change without including any change in irrigated areas came out to about 400 to 1,400 petacalories of present-day production, which is about 8 to 24% of the present-day production. Without including CO2 effects, the effect was much bigger, about 1,400 to 2,600 petacalories of lost production. What we found when we included freshwater limitations implied by the hydrological models and the reduced runoff, these implied that in these red areas, if you add up all of these red and pink areas here, this implied that about 20 to 60 million hectares of irrigated cropland would have to be converted to rain-fed by the end of the century. And that implies a further loss of between 600 and 2,900 petacalories. So you can see a huge range here reflecting the huge range of outcomes of the models, but on the same order, the irrigation loss effect, the lost freshwater effect, about the same order as the direct climate effect, which is interesting. And then finally, in these green areas, these are areas that could actually support a net increase in irrigation, which could actually provide some adaptive capacity to climate change. We did a couple different studies I want to highlight real quick about the importance of CO2, because as I said, CO2, atmospheric CO2 and CO2 fertilization effects are really the crucial, not just the crucial driver of positive climate changes in the future, but also the crucial driver of uncertainty in what we see in the future. So this is a study we did on the impacts of CO2 on crop water productivity, so the unit of water needed to produce a unit of crop output. For this study, we compared the results of our models to the fairly limited set of FACE experiments that have measured crop water productivity at increased levels of CO2. We found fairly good agreement. So the colored bars here are the results of our models for irrigated and rain-fed conditions, and these the triangles and bars are a compilation of the results available from global FACE experiments. You can see again huge uncertainties, but reasonable agreement with what's available in the FACE experiments. Extrapolating these results globally, we found some fairly interesting results, but basically with huge uncertainty. Crop water productivity increases, but with uncertainty on the order of 3 or 4 times the effect. Finally, we also looked at in a later, more recent analysis, following up on a paper that came out last spring from Myers et al. That was compiling some very interesting data from on nutrient concentrations under elevated CO2 from FACE experiments. These experiments showed that substantial zinc and iron decreases in C3 crops studied under increased CO2, as well as protein decreases in C3 crops without nitrogen fixing. So besides soybean, they found also strong protein decreases. And we looked at these analyses and combined them with the EasyMIP analysis from the 2012 Fast Track study. And this is attempted to be summarized in this little set of, these are supposed to be plates. I think these are supposed to be cracks in the plates. But the idea here being that the effects of climate change without CO2 fertilization see a reduced amount of calories, so the size of the plate is calories, a reduced calories by the amount of this red ring under RCP 8.5, whereas under RCP 2.6, the reduced calories is much smaller. When you include CO2 effects, you only have a relatively modest reduction in calories from RCP 8.5, but extrapolating the results from Myers et al., you actually find significant reductions in the zinc, protein, and iron content of agricultural commodity production. So we called this fertilizing hidden hunger, because while we may end up, CO2 fertilization may end up increasing caloric availability, or at least reducing a lot of the negative effects of climate change on caloric availability, it could end up actually reducing the density of essential nutrients in crops, which could have some very challenging, unforeseen consequences. Finally, we combined these results together in an economic analysis using 9 global economic models, again driven by an ensemble of global crop models and global climate models. And I wasn't closely involved in this, but this is Jerry Nelson et al. Paper that appeared in PNAS, and I find this summary plot to be quite interesting, so I'll walk through it briefly. The bar on the right is the exogenous yield change used to force the economic model, so you can see it's between 0 and minus 40. Y tot is the yield change after endogenous model adaptation. So you can see the difference between these two is the level of adaptation that's assumed in these agroeconomic models. You can see increases in area overall within the models, little change in production or consumption, and then finally a moderate increase in prices with the potential for quite a large change in prices. So massive uncertainty, but the potential for quite fundamental and potentially devastating effects on markets. Right now, I want to go through some of the vulnerability factors that a lot of these we've already talked about, but I think it's very interesting and crucial to think about them within an agricultural context. The key point, of course, being that climate change is not happening in a vacuum. We have regional heterogeneity with household systems and poverty and vulnerability, so livelihoods of household systems and subsistence farmers and the vulnerability that induces to them for climate change. We also have large-scale droughts and extremes, which may or may not be increasing or shifting to different regions, and the types and the way that affects vulnerability. We also have serious issues around irrigation and groundwater, and groundwater depletion and availability, and including effects of not just climate change, but also the way that technology and just development demand and irrigation and even adaptation to climate change may lead to increasing depletion of groundwater and increased vulnerability in certain places. And finally, of course, we have population growth and urbanization and food prices, leading to, in some cases, increased vulnerability for urban consumers and increased political instability. So let me just run through those real quick. So this is an example of an AgMIP regional scale vulnerability study. So this is what we call the AgMIP Regional Integrated Assessments. This is a project that is funded by DFID. It's a 5-year-long project. It involves 8 regional teams from different parts of Africa and South Asia. The teams include participants from 18 countries and total something like 200 scientists. The number is always sort of changing up and down as we bring more people on. It includes a massive data gathering, standardization, and modeling exercise that includes climate models, crop models, a multi-model approach at every stage, and economic and integrated assessment and farm system models. This is sort of a little sketch of how each of these regional integrated assessment projects work. So this is the closest I can get to a systems approach to food security, so I had to at least include it, and I'll try to explain it. We take from the global and national level analyses, so a lot of what I've described earlier in the global level work. We take things like prices, productivities at a global and national level, and what we call representative agricultural pathways and scenarios, or RAPs. These are then fed down into these detailed farm system models, and you can't see this very well, but this is a really lovely cartoon of how a specific farm system in, I think, southeastern Africa works, where you can see everything sort of going in different places. You have your cash crops being grown and used to buy fertilizers, and used to buy and the silage being used to feed animals, and the animals producing fertilizers for the cash crops, and your other crops for feeding your families. And it's this really fascinating integrated system, and it's extremely difficult and challenging to model. Finally, we map these to different regions, acknowledging the regional heterogeneity between these different locations. Even with similar farm systems, you can get very, very different heterogeneous responses to these farmers, both from socioeconomic and environmental and climate regions. And then finally, under different scenarios of climate change, these different parts of the regions, these different systems, can map to different places on the distribution of climate impacts. So you end up with some regions, some locations, some farm systems that are winners, some that are losers, and looking at how this distribution evolves and using that to represent vulnerability. And then finally, linking that back to national and regional scale assessments through scaling. All right, but because we were, in theory, supposed to talk about the U.S. a little bit, I thought I'd throw in some U.S. projects in here as well. I want to talk about large-scale drought, and I'll use recent droughts in the U.S. as an example. So we all know that drought is a major problem, so I'll just give a few statistics. Drought and heat events in the United States accounted for about 12% of all billion-dollar disasters in the last 30 years, but about 25% of the total monetary damages. So they tend to be some of the most expensive of all weather-related disasters that we experience. The 1988 U.S. drought is estimated to have cost a total of almost $80 billion, which is behind only Hurricane Katrina as the most costly weather-related disaster in U.S. history. And in fact, once the numbers are all in for the 2012 drought, it may even come out as being more expensive. Finally, of course, just to vaguely say that warming temperatures and sifting precipitation may exacerbate these problems in some areas. I don't want to be too concrete there, of course. It may increase the frequency and/or the severity of large-scale droughts in sensitive areas. Certainly something that we at least need to be prepared for in our risk management and planning. So I just want to throw in a little bit of good news from what we found from this study. in the US. So this was an analysis we did of system-level sensitivity and adaptation. So we did an analysis over the entire US at a high resolution using crop models and technology and climate change and climate scenarios, or historical weather scenarios. And we simulated two counterfactuals within this analysis, one in which we took the 1988 drought using 2012 technology and the 2012 drought and 1988 technology, so basically swapping the two droughts and seeing how they would affect. And we found that at a system-wide level, even though the 1988 drought was actually more severe in terms of the actual production lost relative to the local mean in that time than the 2012 drought was, we found that it was actually, the 2012 drought was actually far more severe from an agricultural perspective. If the 2012 drought had hit in 1988, losses would have been about 29% of trend. The 1988 drought in 1988, losses were about 25%. The 2012 drought in 2012 was about 22%. And finally, if the 1988 drought had hit with 2012 technology, losses would have been only about 18%. Again, this is only a single modeling study, but it points to an interesting improvement in large-scale system sensitivity to drought on the order of something like a 25% reduction in drought sensitivity over the last 25 years, which is certainly an interesting and positive result. So it's nice to have something positive to throw out there, right? Now for the negative part. Of course, we know, many of us know that that groundwater in the U.S. is in not that great of a shape in many parts of the country. So groundwater accounts for about 60% of irrigation and 40% of drinking water in the U.S. And it's expected that many recent near-term in the next few decades trends are expected to put additional pressure on the demand for groundwater. That includes, of course, warming temperatures, changes in management, and adaptation pressures from those warming temperatures are all expected to increase demand, and I'll show some very simple examples of that in a second. However, going back to CO2, increased CO2 is expected to decrease water demand from crops, and so hopefully that could be a silver lining on this. However, we've learned from a lot of recent results, both from open field face experiments and from other sources, that perfect. That some of these are questionable. Just really quickly, this is a prototype experiment we're doing to try and look at some of these technology trends. So we put together, by calibrating our model over trends in the U.S. over the last 35 years. This is planting date trends over the last 35 years. This is anthesis dates, and this is the total growing season length. By calibrating those and extrapolating them into the future, which is under a no climate change scenario, basically what is expected to happen to management. Growing seasons are expected to get longer. Planting dates are expected to get earlier as we get better and better planting technologies. This leads to significant increases in yield, of course, but it also leads to significant increases in demand for irrigation on currently irrigated lands. And this is basically because the growing seasons get longer, you've got your plant out in the field longer, you have to irrigate it more. So even without any climate change, we expect somewhere around 5% increases in irrigated demand, and with climate change, it's much more severe. Is it blinking mean I'm over?
You're right at the end.
Oh, okay. It's about to explode. So more vulnerabilities, climate, urban vulnerabilities. I think most of you have all seen this. This is the correlation of the FAO food price index with various different food riots and other political instabilities from urban consumers around the world. Yet another key vulnerability. Finally, I knew I wouldn't get to my next slide, so I just put a summary slide of all my what's next slides right here. These are kind of a short list of some of the things that are going on next in AgMIP and RIDSEP and EasyMIP, and you can feel free to ask me about any of these things later and how they pertain to what we're doing here. Thank you. No time for questions?
For
No
our
time.
next speaker, we have to do a text switch because they're coming by teleconference, so feel free to come ask Joshua some questions while we do that.
Okay. Well, come on up. Any quick questions, please? Yes, please.
Great talk. Hi, George Luber, CDC. Excellent talk. Really good talk. I'm so glad the organizers included you on this. Now we have two experts, you and Lou Ziska, in the room. So we've looked at Lou's work on pollen and your work on crops. What about other, let's say, natural ecosystems, forests, and their ability to handle all of the CO2? I see greater biomass and other nutrient deficiencies, but what about the integrity of these plants in a high CO2 world?
Don't forget pests.
Oh, yeah,
Yeah.
those too.
Killer ones. That's what's going to kill us.
So I don't know the answer to that. I'm not a forest man yet. Can somebody else want to?
About pests. Pests are the things that are
Well, one of the things I wanted to actually get to, so I'll just fake like I'm answering your question by answering this one, is the impacts of both pests and diseases and especially ozone on crop productivity. I think this is a key area where we might be able to find some sort of, twofers in terms of global policy. Decreasing ozone both decreases, direct health implications due to air pollution and also decreases damage to crops. It's highly uncertain how ozone is really affecting crops, but we know it's bad and we know it could be very, very bad. So doesn't answer your question, but at least it's an answer to some question. We still have time?
So actually my question was about pest biology. Given the constraints on production and quality that pests impose, how did you model the impact of rising CO2 and climate change on pest biology, and how does that change the limitation or the models?
Yeah, so the models the traditional models that are run globally, and in fact, pretty much any crop model you can find, doesn't consider pests in any dynamical way. There's some really, really interesting work that's emerging, especially around locust outbreaks and the effect that climate change and especially CO2 fertilization has on locust outbreaks. Because of the trigger of locust swarming behavior is the carbon to protein content of the grasses that they're eating. And so as you get more CO2 in the atmosphere, you actually get more carbohydrates in the grass and a bigger carbohydrate ratio, which is actually expected to drive more frenzied locust outbreak terribleness behaviors. So
Then
there you go. It's like sugar for...
Quick follow-up question. When you did the modeling of how different crop species respond to CO2, there's a fair amount of work in the literature showing that different cultivars of, say, soy respond differently to CO2, or different cultivars of rice, or different cultivars of wheat and barley. And the degree of response is quite large.
Absolutely.
Did you incorporate that degree of response in the model?
Well, the Myers et al. Paper especially, that looked at the FACE experiments and looked at nutrient concentration.
Hi, this is Dick Jackson.
They did studies across different cultivars, and they found, especially for rice, they found huge variations across rice in terms of the nutrient response at different CO2 levels. And they took that to mean that there's actually some very good breeding channels that could lead to much better responses in rice. But they found much less positive responses in, I think, wheat and soy, which was not quite as promising. But.
Okay.
Do we have a... Are we ready?
One more question.
One more? Okay, one more question.
Yeah, this should be a pretty easily, or at least the first part's an easily answered question. So I've seen a lot of the maps like you've shown that show an increase of production in northern Canada and Siberia and places like this, and a decline in production in the United States. The really easy question is that's relative production, not absolute production. Mm-hmm. Yes?
Yes.
And the second question then is, there are huge implications of the fact that the breadbasket, that production shifts so huge distances geographically. Question one is, are people assuming the same cultivars, or are they assuming some technological adaptation of cultivars for shorter growing periods, for example, and shorter light? And second, all of the implications of transportation and distribution, are those also modeled in these kinds of
So those northern latitude
exercises?
effects are are very complicated. First of all, they mostly end up coming out in the models that don't include detailed soil models. So like the LPJ, the models that came from like the land surface modeling community that don't have really detailed soil models, because the soils up there in the high latitudes just can't support modern agriculture at all. Now, some of the effects are true. You can push up into the 55s and stuff into Canada, and you will get some, you know, 3 or 4, eventually 3 or 4 tons per hectare corn yields up there that may actually make corn either as a silage or even as a grain crop a viable alternative to what they're growing now. But you have to be careful with the results in those far northern latitudes, and because again, we show them as percentage effects. I mean, we saturate that percentage at 50% just because otherwise in some places, yeah, you'd have 3,000% effects. But so there are ways to do it better. What we should have done, the FAO, for example, produces these cultivatable areas maps that actually mask out soils that are that they consider to be just completely incapable of ever growing anything. And we didn't apply that to those maps there. We probably should have, and in the future we will be applying those masks to everything we do, because it is a little annoying when you start to see these super high yields in the Yukon and stuff, and you're like, I don't know about that. That might not be possible. Yeah.
Thank you. Our third speaker, I believe, is on the line, and that's Dick Jackson from UCLA. Title is Urbanization, Climate Change, and Human Health. And Dick, you've got 30 minutes, and I'll give you a signal at 25 minutes. Thank you.